All right, guys, let's settle down and start the next session. Wow, high school teachers settle down so quickly. So much more emotional maturity in this room than in the average conference that I go to. It is my pleasure to introduce Nick Rod. He is a divisional fellow at Lawrence Berkeley Laboratory, where he specializes in the search for dark matter, effective field theory, and collider physics. He was previously a staff member at CERN and a Miller Fellow at Berkeley, and he will be answering the question, what is phenomenology?
Wonderful. Thank you, Rachel. Thanks so much, all of you, for coming along today. It's a real deep pleasure to be able to share some of my science with you and just sort of explain what are the questions that bother me during the day and sometimes even at night. So we've heard so far from Grant what is really the fundamental language that we have in particle physics that describes what are all the ingredients, how do the different ingredients we have interact with one another, and how do we make these amazingly precise predictions that Grant asked us about. But there's another fundamental aspect of phenomenology that really bothers me, and this is to try and understand, well, what are the ingredients that we have scattering together? How do we know that we've got them all, and is there potentially any missing? And so one of the fundamental questions that we worry about is what are the basic ingredients that make up nature as we look deeper and deeper. And we continue to learn more and more about these. Of course, as Grant mentioned, we recently discovered one of them at the Large Hadron Collider, the Higgs. But what I want to do today is take you on a deep dive into the question that I find most compelling, and that is to try and understand what is the particle that makes up the majority of the mass in the universe, and this is something related to dark matter. So this is just going to be one taste of the sorts of questions that we're worried about in particle physics, but hopefully I'll give you a sense of why this is such a compelling problem, and also why we think we have a chance of solving it, I certainly hope, within my lifetime. So at the end of this, just to give you a taste of where we're going, this is one visual representation of what dark matter could be, and by the end of the talk I'll hope to explain to you why there's a deep connection between dark matter and cricket. Okay, very good. So let me just start out by impressing upon you why I find this question of dark matter so deeply, deeply compelling. And really, our modern understanding of dark matter dates back to the pioneering work of Vera Rubin and Ken Ford, done in the late 60s and then published in 1970. And what they were doing is something that at first blush might not seem particularly deep. You might have thought this is something that people did a long time ago. They were staring at a nearby galaxy, actually one of the nearest galaxies we have in the universe, the Andromeda galaxy. This is a beautiful image of it I'm showing you here. And they were studying the motion of objects like stars within the Andromeda galaxy as they rotate around. You can think of this as like the souped-up version of studying the orbits of the planets in the solar system, for example. Of course, historically, that was a very fruitful endeavor, and we learned a lot about that from studying that system. And you might think that there's not much left to learn if you go to larger scales. Like probably it's just going to be a souped-up version of what we understood in Newton's times. So just really to pay homage to the fact that the field that I spend most of my time thinking about was really pioneered by this amazing scientist, Vera Rubin. There's a lot of things that I could say about her life, but I think one of the things that I take away the most is that I just told you that probably you would think this wouldn't be an interesting thing to do. But really the hallmark of an excellent experimentalist is they listen to theorists, but not exclusively. And sometimes they think sometimes they appreciate that, sure, theorists might be very convinced about what's going to happen, but we should probably go and check it nonetheless. And I'm going to give you an amazing example of this here, and this insight that she had that we should look in these systems has really opened up an enormous field that I'm very happy to be part of. So as I said, the idea was to study the motion of these systems as they rotated around the Andromeda galaxy. There will be things that are rotating just like the planets are around the sun. And so just as a reminder, I mean, I'm sure we're all on the same page here. Here's an exactly to scale image of how the Earth moves around the sun. And as we appreciate what's happening here is that the reason that this is going on, what we learned from Newton, is that there's a gravitational pull between these objects, which is what stops the Earth just flying off the screen here. So this was the expectation. We can make this much more quantitative. We can compute what the circular acceleration should be, and then this has to be matched by the acceleration imparted by the gravitational force. And when you solve for, say, what is the rotational speed of these objects, you find it has this form here. And the thing I want to draw your attention to is that as you go further and further out from the object that has mass, the speeds would drop off. So maybe you're familiar with, I mean, regardless of whether you call Pluto a planet, everyone agrees that it is an object that is orbiting the sun. And then what you can check is that the Pluto is moving much, much slower in terms of its orbital speed around the sun than the Earth is. And And the reason for that is that much further out, the gravitational pull is much weaker. And it actually drops off exactly as the square root of the distance as I'm showing you here. So we'll take that insight and we'll move to the Andromeda Galaxy. So if we find something here, it's moving relatively quickly because it's near the center. If we go further out, you can find another object, and the expectation is we'll be moving a little bit slower. And if we manage to find something on the very, very outskirts of this galaxy, what you would find in the end is that you would expect that its speed is starting to get very, very small, just like the Earth is moving much faster than Pluto, for instance. Indeed, we can come up with a quantitative prediction. Look, there's a mess here. We have to know exactly how the matter is distributed in this galaxy, but there are models for that. But the broad expectation is that as you move further out beyond where we can see any appreciable matter in this object, all of the speeds should be tending towards zero. And there's this flip here just because the speeds are going one direction on this side and then it turns around because it's circular motion. So that was what all the theorists predicted, and nobody bothered to measure it until Vera Rubin came along. And the unbelievable result was that the measurement looked nothing like what was predicted. So what I'm showing you here are individual objects that were seen, and then they measured their speed. And the really startling part of that is even when they found objects at the very outskirts of this galaxy, they were still moving essentially as fast as the ones in the center. There seemed to be some violent deviation from this prediction that things should drop off as 1 over the square root of the distance. So this was enormously shocking, and it took people a long time to come to grips with it. But the only way we've been able to understand this is that something else has to be pulling on these. The matter that we can see just isn't enough to explain how this is pulling. And also the matter doesn't seem to be doing that much, because as we move away from it, the speed is essentially unchanged. And so just to sort of sum up what's happening here, if you really have deep faith in gravity as we understand it, what is essentially happening is that it's like the Earth is orbiting around something, but we just can't see what that something is. Now, of course, biologically this would be a catastrophe, but if you had some confidence that gravity really works the way that you think it does, what you would infer is you can't see it, but there had to be something in the center here that is pulling on this planet in order to keep it moving around in a circle. So that is our modern understanding of what's happening in this system, is that there has to be a huge amount of additional mass in here that just doesn't interact with light in any appreciable way, so we just don't see it when we take images of these galaxies. And in fact, that was really just the opening understanding of what dark matter is. Once people realized that there was this missing matter here, they started looking at other systems throughout the universe. For example, they looked in collection of galaxies, for example, in the form of, there's this famous object called the bullet cluster. Again, it's just a pretty picture I can put up here. Then there's this other studies you can do where you can look at the distribution of all matter that we have throughout the universe. You get these beautiful cosmic web images I'm showing you on the bottom left. And then we can also look back at some of the earliest times we can see the universe. This is sort of a baby photo of the universe when it was only 200,000 years old, roughly. So this is the beautiful image of the cosmic microwave background. And when we tease out what's happening here in detail, we find again and again that there seems to be this huge amount of mass there that just doesn't interact with light at all. And so because we can now make such detailed experimental measurements of this, we can actually be quite quantitative. And one fact I can tell you is that of all the matter that we have in the universe, 84% of it is dark matter. And so we know an enormous amount about what makes up the things that we see around us. We understand that as we look deeper and deeper at regular matter, eventually we run into protons and electrons, and as we look deeper we find that, for example, ultimately protons are made of quarks and gluons. But this is telling us that this enormous success that we've had in particle physics is completely restricted to this tiny pizza slice of about 16%. The remainder of this, we have no idea what it is, and this is what we collectively call dark matter. Dark just because it doesn't interact with regular light. So what I'm going to tell you for the rest of the talk is that whatever this dark matter is, it just has to be a new additional particle. So you would think that that's reasonably self-serving for a particle physicist to tell you that. It certainly keeps me in business. But I think there's a deeper reason to suspect that this isn't a crazy idea. At least in everything we've seen so far, as we peer deeper and deeper and deeper, we just keep finding particles. That seems to be the great success, one of the outcomes of the scientific process is the atomic hypothesis, that everywhere you look, ultimately things are quantized and made of particles. It's not a crazy idea that maybe this new form of matter we've seen is just some other particle we haven't discovered yet. And in fact, actually, one of the amazing features is that there's many ideas for what this particle dark matter could be, that when you actually add it in, you can come up with theories where you can do the sorts of calculations Grant told you about and figure out how this interacts, and all of these observations become consistent with the data that we have. The question then is just, what is this particle? So if you want to know something about particles, there's an amazing reference, like a printed version of Wikipedia for particle physics. This is something called the Particle Data Group. It's actually maintained by some of my colleagues at Berkeley Lab, so I'm contractually obligated to tell you about it. So if you go and open this book up, and I very much suggest that you do, you'll find listings of various particles. Some of them you will have heard of, some of them you may not have. Here's one called the B meson. And just to give you a flavor for like what it even means to start talking about a particle, this is the listings that you find when you open this book up. So you find its name, you find some properties about what spins it has, like Grant was telling us about scalars and fermions. There's some bosons and fermions. There's some details of that at the top. But one of the first things they ever talk about is what is the mass of this particle. So you can see it has a mass of about 5,280 in some units called mega electron volts, or MeV. So I'll come back to describe that in a moment. Just to tell you, if you ever have trouble remembering this number, I'm not sure why you would ever need it. I don't even need it in my own work very often. One of my colleagues who literally keeps a copy of the PDG on their bedside table gave me a very easy way of remembering this number. So it actually turns out that the number of feet in a mile, probably most of you know this, is 5,280. But as you may have gathered, I didn't grow up in this country. So I never was able to remember this number. I was never able to remember that number. But the fact that they're the same actually means that unfortunately these are both stuck in my mind. So maybe this is helpful for you. Okay. So as you keep looking through this book, you'll find all the particles that we know about. I mean, for example, actually the B meson isn't a fundamental particle. It's like the proton. It's made up of quarks. But you will also find fundamental particles. And here's another one that you would have heard of, the Higgs boson. And again, there's some words here, something about the spin. But the first thing that they start talking about is its mass. And you can see that the Higgs boson has a mass of about 100 in some different units. Here it's given in the units of GeV. Okay, so then the quest for understanding what the particle of dark matter is at this stage is just reduced to keep moving through the PDG until you eventually come to the dark matter entry. But what you will find at the moment is nothing. So although we're confident that dark matter has to be a particle, we know nothing about, not quite nothing, I'll review that for you today, but there's very little we really know about what exactly its particle properties are. And for all my great confidence that it's some new particle we haven't discovered, I can't yet tell you even the most basic properties about it, like what are its spin or what are its mass, for example. So I want to focus on just one aspect of the question that you would have to answer if I was to stand before you and tell you we know what the particle of dark matter is. And that is, I would need to be able to tell you what is its mass. And then as we dive into this single question about trying to understand what a particle could be, we're going to find that there's a lot of challenges, but also opportunities. Because as we think about the different ways that the dark matter mass could, what the values of the dark matter mass could be, we'll realize that searching for it will be completely different. Okay, so let me just start out by giving you some sense for how masses are measured in particle theory. This is very related to what Grant was telling us about, like physicists like to make convenient choices to make our lives simpler. So of course the normal way that we measure mass is in terms of, for example, kilograms. And the reason for that is that phenomena we see around us in the world then have very natural sizes when we measure them in kilograms. For example, I'm an extremely reasonable weight of around 70 kilograms. So it's a very natural unit to have here. But then if we go to very light objects, like the proton, we have to use very, very small units, because protons just aren't naturally described in kilograms. If we go to very heavy objects like the sun, we have to put some massive factor here, so it's 2 with 30 zeros after it, kilograms, because suns aren't naturally described. They're not things that we run into day to day. So physicists, because we're talking about particles, we wanted to find a new set of units where the particles will have nice numbers. And this is what we usually work on. These are these so-called electron volts that you saw in the PDG. We had a mega electron volt. The proton has a natural, its mass is around something called a giga electron volt. And these are just SI prefixes. A giga electron volt is 1 billion electron volts. What exactly an electron volt is just some historical thing that was defined. It's more just like what exactly is a kilogram. It's just a measure of weight. And it's just a very convenient measure if we're talking about particles because the units don't become so large. It becomes slightly inconvenient if you want to develop a scale that measures human weights in GeV. I'd be a bit alarmed if I saw that when I hopped on the scale in the morning. But that's okay. We can still keep track of this. And then, of course, things naively get even worse when we go to measure, for example, how heavy the sun is in terms of GeV. Again, self-serving, but I would posit that this is a much more interesting way to quote the mass of the sun than measuring it in kilograms. And the reason for this is that we know the dominant constituent of the sun is hydrogen. And hydrogen is a proton and an electron, so most of the mass comes from the proton. So if I tell you that the sun has a mass of 10 to the 57 GeV, I actually know that there's roughly 10 to the 57 particles in the sun. So I've actually learned something about the sun. If I tell it to you in kilograms, you can roughly tell me how many nicks it would take to pack into this thing. But I think there's not very natural. So this is a much more, I think, a useful unit to keep track of things. Because ultimately things are made of particles. That's the reason. Good, so that's what the unit is going to be. Now let me start walking about what could be the possible values for the mass of dark matter. And for this I want to introduce a ruler of particle masses. I wasn't able to buy one of these on Amazon, so I'm going to construct this for you here. So the base unit of the mass is going to be this GeV that we just described. And as we move to the left of the ruler, the particles that we will be talking about will become lighter. And as we move to the right of the ruler, they'll become heavier. So let's start out by putting some particles we've talked about so far onto the ruler. On the lighter end, at 1 GeV, we have the proton, and at the heavier end, we have the recently discovered Higgs boson found back in 2012, which has a mass of about 100 GeV. So this is a start, but what we're going to quickly find is that even within the particles we've found so far, their masses cover an enormous range. So this ruler is going to quickly become very big. And so one thing that is convenient to do is that instead of having a ruler where as you move notch by notch, you go 1, 2, 3 GeV, it's actually very helpful to have the notches move in powers of 10. So here, as I move each notch, here I'm at 1 electron volts, here I'm at 10 electron volts, here I'm at 100 electron volts, 1,000, etc. So this is essentially a logarithmic ruler. And when I write it this way, here at 1 GeV, I have the proton, and now I go up 2 notches, that's 100 GeV, that's where the Higgs is. Now I can very naturally add in other particles we know about, like the electron, which has a mass of about 2,000 times lighter than the proton. And just to give you some sense, you're probably all familiar, but these are the various SI prefixes that I often have to look up on Wikipedia, but they're out there. And so you have a milli all the way up to a peta, and for example, it's the same SI prefixes you have when you're talking about computer memory or all other types of measurements. It's the same ones here. So I just want to give you some context for how much, even just to talk about the particles we know about, how large the ruler already is. So for example, if I tried to use the same ruler to measure currency, everyone agrees the most natural currency to work with is the Australian dollar, and so you would start out at a value of 1. But if you go all the way up here, I'm telling you that this ruler already, not only does it have space to go down to cents, it already can go up to the entire Earth's GDP. So just to give you a sense for scale, just about talking about the particles we know about, we already have a lot going on here. So within this ruler, this is where the masses fall for the particles that we've found so far, the so-called particles of the standard model. Of course, there's exceptions to this, like the photon, we, as far as we're aware, is exactly massless, so it doesn't fit on this scale. But the other particles we know about exist in this range here, roughly from the electron being the lightest, all the way up to, there is one particle a little bit heavier than the Higgs, but the Higgs is around the upper end of this mass range. That's what we thought until some experiments in the last few decades showed that we have these fundamental particles called neutrinos that we thought were exactly massless, but then slowly evidence has emerged that they have a very, very small mass. And I mean exceptionally small. We don't know the exact neutrino masses, but we believe it's about 0.1 electron volts is around the scale. So this is about a factor of 10 million lighter than an electron, which was otherwise the lightest particle. So these are obscenely light particles, although for some reason they seem to have a mass. A question you can ask is, well, why are the neutrinos so much lighter than everything else? The answer is we have no idea. And this is a really active area of research to try and understand what is causing the scale separation here between these two things. It's a very, very interesting question, but we truthfully don't know the answer. And just to emphasize just that, building this up here, I'm going to leave the standard model behind pretty quickly, but just building this up has been an enormous success of the last few decades. And of course, there's various measures of success, but one is a trip to Stockholm. And for example, some of the work here was recognized by Nobel Prizes in the last 10 or so years. Just as a final point, because this will be useful in where I want to go, thanks to an equation you're probably familiar with that was developed by someone famous. I've repeated it at the bottom of the slide if you haven't seen it before. There's actually a relationship between this ruler for mass, and also you can think about this as a ruler for energy. And so just to tell you the correspondence here, if we're looking at around this electron volt scales, then the energy scales we're talking about is exactly the energy scales for light that our eyes the electromagnetic spectrum that our eyes are sensitive to. So that's the optical range. Whereas when we go to the upper end, we're talking about the highest energies we've ever been able to produce as a species. This is what was achieved at the Large Hadron Collider, where they had to get to energies of 1 trillion electron volts, or 1,000 GeV, and this is what was required to produce these very, very heavy particles like the Higgs that we only finally found recently. Okay, so that's just some words about how physicists measure the masses of particles. And I've given you context about particles, hopefully some of them you've heard of, maybe a couple of new ones like the B meson that's sitting somewhere in there as well. What I want to do now is ask the question of what would happen if dark matter existed somewhere on this ruler? Because we'll be able to learn certain things about drawing analogies with other particles we know about to try and think, if dark matter was there, how would we go and search for it? So what I want to start out with is talking about some ideas that I would broadly classify as the dark matter classics. These are ideas that have been around from shortly after Vera Rubin taught us that dark matter existed. We've been looking for them for a while. They may be a little bit outdated, but they're still good. There's still some good aspects of what we're thinking about here. And so we continue to look for them, but they are old ideas. So the first one is something that the community called weakly interacting massive particles, or usually just abbreviated to a WIMP. So what a WIMP is, you can see that the masses tend to be on the heavier end of the particle scale. So that's why they're called massive particles. And the reason why they're called weakly interacting was because if they were strongly interacting, I mean, there's caveats to this, but we probably would have seen them so far, okay? So the fact that we haven't seen them means that if they talk to us, they have to do so very, very weakly. So the question is, let's say dark matter is somewhere in this range. How would we be able to find it? Well, again, we know a lot about particles. Yes, we don't know what dark matter is, but as Grant explained to us, we understand a lot about what particles can do, and we can compute how they interact with various things in exquisite accuracy. So we can maybe draw some analogies to the ways that we understand other particle interactions to think we could look for things like the WIMP, for instance. And just to give you a flavor for there's been a huge industry of searching for WIMPs over the last few decades. One of them is you could look for WIMPs actually being produced at the Large Hadron Collider. It might have enough energy to produce this state. You would think, how would you see dark matter? It's an amazing, these searches are amazing. I don't know if this was mentioned to you yesterday, but what would happen is you'd see some things come out in your collider, but there'd be a whole bunch of missing energy. So if we're really confident energy conservation works, you'd see some particles flying out and nothing on the other side. And if you really trusted your detector was working correctly, and of course that's a very challenging thing to do, but there's some amazing people working on this, then you could infer that dark matter was being produced and flying out the other side of your detector, for instance. So that's how dark matter detection could look like at the LHC. Amazing searches have been done for it, sadly nothing so far. Another thing that we could do is that Vera Rubin taught us that galaxies are embedded in this large halo of dark matter. But if I'm telling you that that halo is made up of particles, then what should happen is that there's just a gas of these dark matter particles all over the place. We just don't see them because they don't interact with light and they don't interact with us very strongly. But what if we built an extremely sensitive detector and we looked for occasionally a dark matter particle flying through and just scattering like a billiard ball scattering off one of the particles that we have in that device? This is a huge research industry called direct detection, and we've looked for these sorts of scatterings so far. I think it's a very interesting way to pursue, but so far nothing definitive. So these are two ways people have been investing a lot of effort in terms of looking for WIMPs, but we haven't seen a signature so far. That's one idea of these dark matter classics. Another idea of what could be dark matter is something called a sterile neutrino. So I don't know how much you know about neutrinos. I just told you that they're very light. But actually one of the other properties neutrinos have is that they're not charged under electromagnetism. So they're also dark in some sense. And actually for a while, people thought that neutrinos might just be the dark matter. They have many of the properties you would want for this. We know that they have mass, and we know that they don't interact with light. So that seems like it's got some of the qualities you want of dark matter. It turns out that when you run the numbers, the neutrinos are just a little bit too light to be dark matter. The reason for this is that they're fermions, and there's this principle called the Pauli exclusion principle, which stops fermions from sitting on top of each other or stops tables just collapsing into the ground. But the Pauli exclusion principle, when applied to dark matter in a galaxy, says that you can't just squish all of these on top of each other. So unless they're heavy enough, you just wouldn't be able to make up the explained mass of the galaxy. There's a lot more that goes into that, but you can actually come up with a rigorous argument that neutrinos cannot be dark matter. Nevertheless, If you had a heavier neutrino we just hadn't detected yet, and it interacted very weakly with it, which is why we call it sterile, that actually is an excellent dark matter candidate. And given that neutrinos are so puzzling and there's a lot of mysteries here, maybe there are more neutrinos out there, and that's a very serious idea that people have considered. Okay, again, let's say that that is the dark matter. How would you find it? Well, there's various analogies we can draw with particles we know about. To give you one thing regular particles tend to do is they tend to decay, many of them. Very few are stable like the proton or the electron. And for example, if you get a neutron in isolation outside of a nuclei, it decays relatively quickly through this process here. And so other fundamental particles could decay also. And it turns out, using the types of tools that Grant taught us about, you can just compute that this sterile neutrino would interact. These are the sorts of blobs that Grant was drawing. You can compute these in quantum field theory, and you find it would decay to a photon and one of the regular neutrinos we have here. Okay, so let's say that could happen. What does that mean? What can we do with this? So let's go back to the Andromeda galaxy that we started out the talk with. And the idea here is that if dark matter is made of sterile neutrinos, if we zoom in on some little part of this galaxy and we put our dark matter goggles on, what we will see is a bunch of dark matter particles flying all over the place. Okay, we can't see that because we don't have dark matter goggles, but what these decays do is they allow us to essentially tag where this dark matter could be. Because occasionally one of these particles would decay to a photon, and then if we look for those photons, regions of dark matter should start to be lit up by these occasional decays. So that's how the search would go. And then there was an amazing landmark result in this field about just over 10 years ago by Ezra Bulbul and her collaborators, where they looked at a distant galaxy which has a huge amount of dark matter in it, and they saw the following. They were measuring the energy of the photons they were getting from this galaxy and how many they were getting. Their prediction was what they should see something that's in red, and you can see there's a very a subtle deviation from this at around 3.5 keV, okay? And so this, for a time, was thought that this could be the discovery of sterile neutrinos. I mean, maybe this plot doesn't get you, I don't see anyone jumping out of their seat, but at the time this was released, this was really a landmark result because people thought sterile neutrinos could be dark matter, and this could be literally the smoking gun excess for what that could look like. And just to tell you why we're existing around here, I told you the sterile neutrino has a mass of around a keV. So if it decays to a photon, you'd expect the photon energy to also be around keV. That's why we've got this scale here. And it turns out keV is 1,000 times an electron volt, so it's much heavier, much more energetic than the optical spectrum. You technically needed an X-ray telescope to do that. And we have very good X-ray telescopes, and they're able to make the sorts of precise measurements I'm showing you here. So was this the discovery of dark matter? And it very well could have been. It certainly got me excited. It got me excited enough to go and think, is there any other way we could test this idea? And one of the ways you can think about cross-checking these things is that this measurement was done by staring at some distant galaxy. But I told you that all galaxies have this halo of dark matter around them. And in fact, we're living in a halo of dark matter. And what that would mean is that the particles that are around us should very occasionally be decaying and giving us these X-ray photons. And so our prediction was that if you took an X-ray map of the Milky Way, it should light up something like this, because there's more dark matter in the center, and then it slowly dies off. So it was a challenging thing to search for, but once we realized this, we went and got the experimental data and looked if we could actually see the Milky Way lighting up. And sadly, thanks to the work that I did with some fantastic collaborators, we didn't see any such discovery. I mean, this was not what we were hoping. We were very much hoping that we would be able to give a strong confirmation that this actually was the dark matter. But sadly, we did the cross-check and it wasn't. So then the question's left, what was that line that was seen there? That's a long discussion I can tell you about. But also maybe to give you a sense for how science actually operates, of course, it wasn't just like everyone immediately accepted what we did. This was one article you can read about the back and forth over this. I can say we never actually came to blows, but there was some heated emails exchanged. I will say it that way. Nevertheless, I think where we ended up is that broadly the community now agrees that this, whatever it was, it could have been the discovery of dark matter. So this gives you a flavor for how that could proceed. But we're all skeptical people. We really want to know that not only to find dark matter, but to know that we haven't fooled ourselves, that we've really done it correctly. And so this is how science often proceeds, and it's sometimes a bit messy in detail. So that's a sense for what's been happening on the search for these dark matter classics particles. I think that they're extremely well motivated, and it very well could be that a sterile neutrino or a WIMP could yet be the dark matter of our universe. Nevertheless, the state of the field is that we've been looking for them for decades now, and you have to show some humility. Nature is telling us that sort of the minimal versions of these just haven't shown up in our experiments. So it's always a possibility that these particles just interact a little bit more weakly than what we thought they did. And so as you look deeper and deeper with these experiments, you'll finally see something. And so there's big programs to extend these searches even further. But I think it's also a very healthy attitude to ask, well, maybe dark matter isn't in this mass range. Maybe it's something else. And if that's the case, then the way that we've been thinking about it might just be not quite correct. And this is really a new way of thinking about the search for dark matter that the field has gone through in recent decades. And I want to tell you about that now. So the goal is to think this is the classic window. How can we broaden that even further? And as we move out into the wild west of particle masses, I want to use two key facts to anchor our discussion so that we can at least keep some connection to reality. And the first one is that actually locally we know quite a bit about how much dark matter there is. I showed you at the very outset the way that we first inferred that dark matter had to exist was on this gravitational pull on stars and galaxies, and it was larger than what we could attribute to all the matter that we know about. In fact, we can do the same detailed studies now in our own Milky Way, and what we've learned is that if we look at how much matter there is around us pulling on the stars, there has to be some dark matter locally, and it's about 1 proton worth of mass per cubic centimeter. So that is to say that if the dark matter had a mass of 1 GeV, which is the mass of a proton, there'd be many, many of these particles in the room. There would be 1 every cubic centimeter. They're just very, very hard to see. Nevertheless, if the dark matter is heavier, you're going to need fewer of them to make up the density. If the dark matter is lighter, we're going to need more. Okay, so we'll keep track of that. The second key fact that's going to be very useful is some basic property of quantum mechanics, which is essentially wave-particle duality. So in our classical description of the world, we really like to classify things as either behaving as waves or we like to think about them as behaving as particles. But what quantum mechanics teaches us is that that's really just a classical way of viewing the world. Everything is essentially both. And every thing that you think is a fundamental particle, if you stare at it carefully enough, you'll eventually see it has some wave-like properties as well. In fact, we can be somewhat quantitative with this to say that as the particles get heavier, their intrinsic size gets smaller, and as the particles get lighter, their intrinsic size gets larger. There's actually another, if you haven't heard about this before, there is one case where this manifests, where you've probably got some familiarity with it, and that's in the electromagnetic spectrum. We know that that light is made up of photons, and as we make the energy or the frequency of those states lighter and lighter, we eventually get into the radio band, and you normally think about radio as waves. In fact, it's usually just called radio waves. But as we make the energy higher and higher, eventually this wavelength is getting smaller and smaller, and the description of them as waves doesn't become very convenient. And that's where we think about, for example, individual X-rays or individual gamma rays flying throughout the universe. They're two ends of the same concept. All that's changed is the energy, or if we move to a particle, all that's really changed is its mass. So I want to make use of these two key facts as we start broadening our horizon about the dark matter mass range. But again, just to emphasize, already this is an enormous scale of particles. For various masses, I showed you can fit the entire Earth's GDP on this. Good, so the first direction I want to go is I want to move these lighter. Now, technically, I can say some more words about this if people are interested, but I already told you there's challenges if things are getting lighter if they're a fermion because of this Pauli exclusion principle. But there's other particles we know about in the universe, like bosons, like the Higgs is a boson, also the photon's a boson, and there's no problem about making bosons lighter. So if dark matter is a boson, we could make it much, much lighter. And so what's going to happen if dark matter is much lighter? Well, let's exploit the two key facts. So the first one, I told you we have about a proton's worth mass per centimeter cubed. So if I make dark matter much lighter, the number of particles in a cubic centimeter has to go up and up and up in order to make up that same matter density. But a second effect will be occurring, and that is that the sizes of the states will be becoming longer and longer because their intrinsic wavelength is increasing. So we're going to have more and more states in a region, and we're going to have their intrinsic sizes getting larger and larger. What happens is that eventually you shouldn't think about having a gas of particles flying around the Earth. You should think that dark matter is behaving like some large-scale coherent wave oscillating through us. So you can already see that this is an enormous paradigm shift in terms of how you would think about dark matter. Previously, if you're looking for some particle to come in and scatter off your detector, well, that's not going to happen if instead you just have a wave passing through the Earth. So you can imagine that you need to think about searching for dark matter completely differently in this part of the parameter space. In particular, you can start asking very quantitative questions about how would you actually look for this type of dark matter. Because any one particle is going to be too weak to detect, but there's some coherent oscillations of all of them that we might be able to exploit. In fact, there are specific models of particle dark matter that actually, although dark matter doesn't couple to light very strongly, or we would have seen it, we believe it actually could very weakly couple to electromagnetism in this wave-like regime. So actually, you might be familiar with the laws of electromagnetism, or Maxwell's equations, which have had a reasonable amount of success in the last 100 years or so. So the claim of this axion dark matter is that Maxwell's equations are wrong, they're missing a term. So the Ampere-Maxwell law gets augmented by some piece that is non-zero if you have an axion or this wave dark matter oscillating through the Earth. But then you can imagine, well, we really do understand electromagnetism in obscene detail. So if there is this tiny little modification to it, we could hope to build an experiment in the lab and try and see if there's some deviation from what Maxwell told us about the interaction of light. And one way that we know of looking for waves, at least that I know of looking for waves, is to build a radio. For instance, of course, this is literally what is happening in the EM spectrum. We fire EM waves throughout the Earth, much to the annoyance of radio astronomers. And what we're able to do then is by tuning our radio to the right frequency, we can pick up the signals that are being beamed out there. And we can amplify one particular signal, even though there's all the signals that are going out there with a device like a radio. So one of the experiments, this is a literal logo, I didn't make this, for one of these instruments is called dark matter radio. And their idea is that they're tuning in to try and find the frequency of the dark matter mass. They claim they can move to AM, FM, or DM. I can tell you, you pick these all up at the same time, unfortunately. And most of what these experiments have found so far is, for example, AM frequencies. But the idea is that you could build a very, very sensitive device and actually look for this. So to give you even more concretely, what does one of these experiments look like? So one of the prototypes of dark matter radio was some acronym called Abracadabra. I can explain what that is if people care. It's a broadband resonant approach to cosmic axion detection with a B-ring apparatus. Anyway, yeah. My colleague who proposed to his wife through a New York Times crossword puzzle came up with that, so okay. So this instrument was a prototype version of dark matter radio, and it was based in a lab in the basement of MIT where I did my grad studies and I worked on this experiment. And this isn't actually the experiment. This is the device that cools the experiment down to make it very, very cold. And then what you're seeing here is just a ton of shielding to keep as many of the radio signals out as we can. Actually, the device is a little thing about the size of a grapefruit within that. So it was a very small device. This was just a prototype to check if these things work. And then once we got the first data, what did we see? We saw something that looked like that. Okay, and roughly what I'm showing you here is what is the frequency of the dark matter, or the radio frequency we're searching for, and then how much power did it deposit in the device. And you can see, just to give you a taste, real data is actually quite messy. And so just to say some things that are going on here, you could ask, is every single one of these spikes some contribution from this dark matter wave? We checked that. We don't think that that is the case. In fact, there's all sorts of complications here. Down here you can see that the power is going up. This is just due to people walking next to the lab, and that imparts various vibrations, and that's something that you pick up in these devices because anyway, this is what happens. On the upper end you see that there are these funny peaks. I have no idea where these are coming from, okay, and nor do my experimental colleagues at the moment. This is something that we're trying to understand, but this is a sense for what happens when you look at real data. We checked, we don't think there's any sign of wave dark matter in this, but there's a lot we're learning about this data, and the idea is, once we've understood this, we can try and shield this better, make an even better version of this device, then push down, and we will see a whole bunch of new things we have no idea what they are, and then we'll slowly understand that, and once we have confidence, the hope is we could eventually maybe pull out a real signal of wave dark matter. It's a messy business, but this is the game that people are playing at the moment. So just to give you a sense for what the challenge is if you're looking for these wave dark matter candidates, so basically we understand how to build these devices. The fundamental challenge is that there's a lot of radio stations to search through. You can actually check there's about 20 million. So what we need to do is we need to set the device up, turn to one radio station, listen very carefully, move on, okay? And you need to do that 20 million times. So this is something that is challenging, but my experimental colleagues are amazing, and they have a lot of confidence that they'll be able to walk through these radio stations in the next, hopefully, decade or two. And so if this is what the dark matter of our universe is, it's going to be a challenging endeavor, but I think we have a well-defined approach to actually testing this question. Okay, so next what I want to say about is, you can see as we went lighter, I just sort of stopped somewhere. Technically, I stopped at a nano EV, which is 10 to the minus 9 electron volts. But you can ask the question, why did I stop there? Could I just keep pushing and pushing and pushing? What's the lightest that dark matter could be? I mean, could it be essentially all the way to the massless limit? Well, we know actually that that's not the case. And we can actually understand this by going back to our second key fact, and that is that essentially every state has some intrinsic wavelength associated with it. As we make it lighter, that wave will become larger and larger and larger. So we really have to go down. In fact, we have to go beyond where humans have defined SI prefixes. I don't know if there's some sort of organization that can add new SI prefixes, but anyway, we may need to go there eventually. But so this is, I think, a zeta EV is 10 to the minus 21 electron volts, and we know that dark matter should be heavier than 10 to the minus 22 electron volts. And the reason for that is that if it was any lighter than that, the spatial scale of dark matter would be bigger than galaxies. But we see galaxies, and we know that dark matter is the dominant matter contribution to them. So if the wavelength was too large, it would just wash galaxies out. We wouldn't even have galaxies in the universe. So it's not maybe the strongest bound that we have, but this is something we know. You can't go arbitrarily light because that's inconsistent with what we've seen in observations. In fact, exactly where this limit is a very heated debate. Some people claim you can push it all the way up to 10 to the minus 20. There's a lot of work to try and understand down what's happening down here and how far we can push this up. But nonetheless, there's a lot of room between here and there. And broadly, if you wanted to look for dark matter in this regime, you've got to look for some sort of wave-like phenomena, like I told you in our searches using these radios. So that's telling you about what's happening on the light end. Now let me ask the question, how heavy could we go? If I want to go heavier and heavier and heavier, is there some sort of similar limit we will run into, just as we did on the light end? So again, I want to exploit this second key fact and think about what's happening. On the one side, as we made it lighter, the wavelength was getting larger and larger. If we make the particle heavier, it will get the size of it will get smaller and smaller and smaller. But we're also putting more and more energy or more mass into a smaller and smaller space. So maybe you can guess, like there has to be, this game cannot go on forever. If you try and put more and more mass into a smaller and smaller space, we've learned that eventually you create a black hole. And so there's a limit that if the dark matter particle was heavier than 10 to the 28 electron volts, it wouldn't be a particle, it would be a black hole. There would be no distinction between the two. So there's literally a hard limit on how heavy a dark matter particle could be. Now, of course, you could say to me, sure, but why couldn't dark matter just be black holes? They're also not very strongly interacting with light. And the truth is, yes, dark matter could be made of black holes. And actually, you can go play this game even further, and eventually there's still another limit. But maybe let me just focus on the particles for the sake of today. There's very interesting searches you can do if dark matter is made of black holes, for instance. Nevertheless, now that we've opened up this heavy window well above any particle we've seen about, or even this classic window, you can ask the question, how would we look for these heavy dark matter states? And let's go back to our first key fact, was that we know roughly around us there's about 1 proton worth of dark matter mass per cubic centimeter. If we make the dark matter as heavy as this Planck scale up here, is what it's called, this 10 to the 28 electron volts, instead of having 1 particle per cubic centimeter, we would have 1 particle per 10,000 cubic kilometers. So in this case, the dark matter becomes a very rare state. They're not passing through you very often. There's not one in this room. And you really have to look very carefully if you're going to see them. But there's one way that they could show up. And that is that, remember that I told you that we generically expect that particles can decay, and that was true of the sterile neutrino. It's also generically true of these heavy dark matter particles that they could decay. And you can compute how much energy is released when a particle with 10 to the 28 electron volts decays. It's actually equivalent to the amount of energy that's released when 500 kilograms of TNT is exploded. But I mean, this is the energy being released by one fundamental particle decaying. So it's just obscene how much energy comes out. And then the constituents that it decays into will be flying throughout the universe with extreme amounts of energy. So the way that you might be able to detect this, and in particular, you can check that you could easily produce protons with the same kinetic energy as some of the fastest cricket bowls that have ever been bowled, which is, of course, of great interest to everyone here, I'm sure. And what you would be looking for is these obscenely high energy proton cricket balls flying throughout the universe, and for instance, they could eventually hit the atmosphere of the Earth. It would lead to a slightly less dramatic event than what I'm showing you here. But broadly, when a super high energetic particle hits the atmosphere, it'll interact very strongly and it'll create a shower of light and particles that you could maybe hope to look for on the Earth. So how would we do this? Well, we could just build a big telescope to look for that. And in fact, the premier version of how you would want to look for this is something called the Cherenkov telescope array. And this is actually about to come online. So I'm showing you here one of these telescopes that you just point at the atmosphere to try and reconstruct the shower of states that happens when a very heavy, very energetic particle hits the atmosphere. That's a real telescope. The right is an artist's rendition for what the full array will look like. And so actually, the first version of this device should start to become fully operational next year. And the hope is that as they start to map out what are the highest energy states that are hitting the atmosphere, we might eventually be able to see some signature of heavy dark matter. So I actually spent a lot of my time recently thinking about this Cherenkov telescope array because it's about to happen. It's a very exciting instrument. And I think there's every chance that when it turns on, you might actually start to see some hint of very heavy dark matter, for instance, in its data. So that's just a quick run through of the various types of masses that dark matter could have. And just to come back to the outset, remember that the basic point here is that if I really claim that dark matter is a particle, I have to tell you what its mass is. But you can see, although I have great confidence for that dark matter is a fundamental particle, I have very little confidence about exactly where its mass could live. There's an enormous range of possibilities. But also, across this range, there's an enormous amount of opportunities, because there's completely different experiments that we could build to look for this type of dark matter. And I think that now that we've been broadening our horizon for how you look for this type of dark matter, we're getting a better sense for really opening the possibility that a discovery could be any year now. I'm very optimistic about this. And maybe just to step back some more about this broader question about what phenomenology is. This is just one of the searches for new states that we have in the field of particle physics. There's many others that are going on. I'm just particularly passionate about this one. But it gives you some sense for what, at the end of the day, we make predictions, we add some new particle in, we go and do detailed calculations of the form that Grant taught us about, and we'll hear more about this afternoon, to actually see what would show up in an experiment. But ultimately, this thing has to be tethered to nature, or it's not really clear what we're doing. And ultimately, it's going to be an experiment that will be the ultimate arbiter on exactly what dark matter is and what are all of the building blocks that we have that make up the universe. Okay, let me leave it there. Thanks so much for your attention.
All right, thanks, Nick, for the great talk. Any questions for Nick? Wow, quite a few. Let's go maybe hear someone who hasn't gone before. Yeah, great.
Thank you for sharing with us. You mentioned axions just briefly and then kind of went off from that. Can you explain more about axions and also the idea about dark matter being in halos as opposed to just permeating all around?
Good. So coming to the first one, I don't know if you're familiar with the Axion laundry detergent. Okay, good. So that's actually where the name of the particle comes from. And so there was a long-standing issue. So Grant mentioned that we have several long-standing issues in physics. One of them is like, why is the Higgs so light? There's another one, which is that the strong force seems to be missing certain interactions that we think might be there. And this is something technically called the strong CP problem, but the QCD force we would generically predict, it would give rise to certain properties of particles, and no matter how hard we've tried to look for them, we've never seen them. And this is just a big outstanding problem in particle physics that we learned can have a resolution if you add some new particle into the spectrum we know about called the axion. It will actually forbid these types of interactions from showing up. What was then realized not too long after, I think potentially Srednicki, who was the author of one of the books Grant mentioned, was involved in this. They realized that particle that was introduced to clean up this problem with the QCD interaction, that's why it was called the axion, also could be dark matter. And then when you computed it some more, you realize if it was dark matter, it had to be super light. And actually, it was expected to couple to electromagnetism in the way that I showed you here. So we're not completely pulling things at random out here. I mean, sometimes we do, but most of the time you try and anchor like the ideas that you have that maybe there's other hints we have from the universe around us that are telling us that that's a good reason why that could be the dark matter. So honestly, I could say a lot more about the axion, but let me leave it there for the moment. Coming to your other comment about the distinction between this gas and this wave, it's really what we know is that galaxies, a majority, like our own Milky Way, about a factor of 10 there's about a factor of 10 more matter in dark matter than there is in regular matter in our galaxies, for instance. And then the question is just how does that behave? Now, if it's a bunch of particles, we know they should be relatively weakly interacting, and so it actually will just behave like the gas in a room, for instance. So the particles will just be randomly flying all over the place. Eventually, as they get too far out, they'll be pulled back in by the gravity of the galaxy. They'll be pulled back in, but they'll just be moving around randomly near us locally. However, if we make it very light, if you want to make up the same description, eventually it's much more natural to think about it as, you know, a whole bunch of radio waves moving all over the place. It's a bit counterintuitive because light is massless, so it's like a massive wave that's moving around, but they're confined to like some region of the galaxy. So it'd be like waves moving around in a box. Eventually they'd hit the wall and come back. But these are two different descriptions of the same phenomena. Again, I can say more, but maybe that gives you some sense.
All right, more questions? Maybe over here.
Thank you very much for all that explanation. I'm just going back to the idea of the mass being 1 proton per cubic centimeter. Is that like a local density, or is that a density that's throughout all of space? Or
Yeah, great question. I was a bit vague on that. So I'll tell you the dirty truth. Locally, we don't really know, okay? Actually, because you think about it, 1 proton per centimeter cubed is not a lot, okay? In the Earth, there's significantly more than 1 proton per centimeter cubed. It's usually in units of something like Avogadro's number, for instance, which is quite a bit larger than 1. However, if you look across the solar system, the Earth is a significant overdensity of regular matter. Most of the solar system is empty, and in fact that's true of most of the galaxy. So sort of what happens is that here it's pathetic, it's very hard to detect, but it just keeps adding and adding and adding where there's not like Earths everywhere. So eventually the dark matter overtakes, and what we can do is if we look at regions of order hundreds of light years, we can see that all of that dark matter added together is enough to actually have a measurable impact on the stars with the degree to which we can measure them at the moment. So this 1 proton per cubic centimeter is averaged over several hundred light years, and then we extrapolate it down to the solar system and hope that we're not in some freak underdensity, or many of the experiments I'm telling you about will be in trouble. But we generally don't think that that would be the case. However, more broadly, as we start to look over the scale, like the scale of the Milky Way is thousands of light years, not hundreds of light years. As we move towards the center of the Milky Way, the density should be getting bigger and bigger, just like, you know, things are gravitationally pulled towards the center loosely. And as we move further and further out, it'll get lower and lower and lower. So that's some sense for what's being measured.
All right, more questions? Maybe on this. Oh, all right, go here.
So just looking at this continuum, right, for the mass, is the school of thought more it's going to be a heavier thing, like more massive or more wave-like, or is that also with like the wave-particle duality thing? So,
no, good question. Yeah, I think as you learn quantum mechanics, this is a question you really grapple with. And I think maybe it was in Feynman's textbook I read about this. I think probably the best answer is that ultimately this is just quantum mechanics, okay? And this is some struggle we have trying to match our classical intuition onto what is just a prediction of quantum mechanics. And quantum mechanics says that everything has, in some senses, particle and wave-like properties. It's quantized, like we can create 1 photon, so that that's like the particle thing. But these 1 photons can undergo all sorts of wave-like phenomena at the same time. So what essentially ends up happening is that in certain cases, one description can be more convenient than the other, but they're always both really there. Like to get this black hole state, I needed argument. I needed to keep track of the size of it as well. Even though the size was getting very small, that was important too. So it's more a statement that it's a particle and wave everywhere. But as you get very light, it's just very inconvenient to talk about, you know, millions and millions of individual particles. They actually behave more like a wave in that sense. So it's in certain cases one description's better than the other, but they're always both truly there.
Since with heavy dark matter, the density of particles would be lower, what would the frequency of events, like of a decay hitting Earth, be? Good.
So yeah, again, in the spirit of complete honesty, we have no idea, right? If we could make extremely sharp predictions for what this would be, then the whole enterprise would be somewhat easier. What we can say is that we have some theoretical prejudice. There are certain cases where we can actually think this would be a very nice range for this parameter to live at, and we've looked for that. And for example, this is something that we've done a lot for WIMPs, where we thought in many of the WIMP ideas where we really try and make it rigorous in the way that Grant taught us about, you can then say this is the rate at which we should see events. And we've looked for it and we haven't seen them at that level. And so what happens is people go back and like, oh wait, actually there was a very easy way that this could have been different, and then you have to look a bit deeper, and that's this game that goes on. So it's in cases we can make predictions, but we always have to be humble and realize that maybe we're missing that. In terms of at that heavy end, you can check that I think you will get one particle moving through a meter cubed area per year. So it's rare, but it's still possible that you could build a detector on Earth and see it. For the decay, actually, what I was actually talking about here is you don't need it to be on the Earth. These decays can just be happening throughout the universe, and this would be a source of obscenely energetic particles that you could look for. So yeah, the decay doesn't have to be on the Earth for us to see it because we can look out into the cosmos. Yeah.
You said that it's either wavelength or heavy, but could it be both?
Good. So maybe just to confirm, your question is could you have both at the same time? Yeah, absolutely you could. And so, of course, if you think about this, if I told you I showed you that pie chart at the very beginning where dark matter was the majority and what we know about is 16%. And as we've understood, the 16% is made of many, many different things, okay? And so you could ask the question, is the same true of dark matter? And ultimately, we think that's probably the case. However, even if we look at the regular matter, of course there's a lot of complexity, but throughout the universe, 75% of the matter is hydrogen and 25% is helium, and everything else is basically in the rest. So if you didn't know what regular matter was, just looking for the hydrogen particle, or essentially the proton, would have been a very successful strategy. So the broader expectation is that within the dark matter sector, there could be, I think this is often called like the cocktail phenomena, where you have many of these at the same time. And that's generally what we expect. But probably one dominates, just like it does in the regular sector. And of course, again, like on the Earth, that doesn't seem like it's the case at all. But if you look at the universe as a whole, which is often what we're doing here, it's much more boring in some senses than what's here, because most of regular matter is basically hydrogen. So that's the strategy. We just try and start to see, one hint of what's going on. But I think if we started to see some hint of a wave, we can actually measure how much of the local density does it make up. And if it doesn't add to 100%, or it adds to like 70%, maybe it could be a WIMP and an axion at the same time, for instance. People keep this in mind, but I still think one at a time is a sensible search strategy for the reason that I mentioned. Great question. Thanks.
I'm not sure that my question's really well formulated, but it's around the idea of dark matter clumping. So with these different types of dark matter, and we think about maybe galaxy formation, how do these different possible types of dark matter clump enough and shed velocity in order to clump? And does it have to be through electromagnetism or not?
No, that's an extremely well-posed question. And in fact, that's something that people think about quite carefully. So actually what we believe is that as we look back out in the universe, we're looking back in time. And eventually what we see, for example, when we're looking at the CMB, is that the universe was a lot hotter than it was now. So essentially our understanding of this is that the universe expands, things cool down, and at a microscopic level, that means they start to move slower. So the dark matter initially was potentially moving around too quickly to clump gravitationally, but as the universe expands, it will cool down, eventually to a level where it collapses. Now we do not think, so regular matter can cool even further by shedding light, which is a way of losing energy, and that then flies off to well away from that thing. We don't think dark matter does that. And in fact, I didn't go into this, but like in galaxies, we often see that they collapse all the way down to a spiral. It can't collapse all the way to the point because of the conservation of angular momentum, but it can collapse down to a disk. We don't think dark matter does that because it cannot shed energy the way that regular matter does. So we generally think that it's like a sphere around with, like, for example, in the case of a spiral galaxy with like a disk in the middle. But then you can ask questions like, well, what if you add a small amount of dark matter could occasionally shed some states? Could you get modified predictions of this? People think about this in detail. It could be that some fraction of dark matter did form a disk, for example, and I believe there's even a popular science book entitled "Did Dark Matter Kill the Dinosaurs?" Yeah, okay. So the idea there is that some subfraction of dark matter formed a disk. If there's a disk that's impacting with our own disk, it would also impact the orbits of asteroids. It would increase the likelihood that an asteroid hit the Earth. So, I mean, there's a few steps in that chain of logic, but nonetheless, these are the sorts of things that people actively think about. And on the wave-like end, you would absolutely change structure formation. Like one of the things you can look for is that certain structures just won't exist. As we try and look for smaller and smaller galaxies, like for example, in our own Milky Way, there's the Magellanic Clouds that people have known. These are like little galaxies that are orbiting around our own. As you look closer and closer, you find more and more galaxies. They just get harder to see because they have fewer regular particles in them. But eventually, if we keep looking and we see that the structures stop, that might indicate that a wave was washing them all out, for example. So yeah, there's a huge enterprise. I mean, not only is it a well-posed question, it's a question that many of my colleagues spend their whole career trying to study. So it's a very, very interesting thing to think about.
Hi, it's such a great and informative talk. So first, just thank you. That's really good.
Thank you.
I'm wondering about the gap there between wave-like and the classics, and like if there's current experiments being done in the search for, I notice it's in the neutrino band. So are there current neutrino experiments being run now that are also looking for dark matter?
So there is actually, I don't work on it, so I have a slight prejudice against this, but there are people thinking, there are people, I don't mean to be too dismissive, there are people thinking in this gap here. It turns out that actually this window around here, our prejudice for the nice models that we like to write down generally doesn't populate this space. There's quite technical reasons that the things either want to be quite light or they want to end up living up on the heavy end here. For example, I told you, like, if you just had a neutrino, it doesn't work because it's too light. So you have to go to a boson, but then when you do bosons, they often end up being much lighter than this here. Nevertheless, there are ways to make it work. And so there are, I know of one. For example, if you tried to look for things that have EV energy gaps, one of these things like molecules or atomic energy levels, and there are people looking that occasionally, very rarely, dark matter might come in and excite at one of the energy levels of these systems. And if you really again, it's all about understanding your backgrounds. If you really understood this, that might be a path to detect dark matter. There's also a broader push for driving these classic candidates down to lighter and lighter masses. So there are ideas here. This is just my own prejudice that I didn't fill this in. But I also think there's a slight prejudice in the field that it is somewhat hard to get dark matter there, but nature will be the ultimate judge of that. We could be wrong. Yeah.
Maybe one more question.
So, sorry, two questions. One, the dark matter radio you talked about, any thought of using AI to go through the 20 million channels? And then the second question, is there a good textbook you would recommend for a high school, community college level on particle physics?
Good. So let me start with the easier question, which is about dark matter radio and AI, no, for me at least. So if you come to it, like obviously there are many challenges about the analysis of these things. And actually, as these analyses get more and more sophisticated, our colleagues are more and more often turning to AI. Maybe you heard this yesterday. For example, probably the most complicated experiments we do in particle physics are the ones at the LHC. I mean, you look at that, the event displays for when all the jets are coming out. It's very hard to tease out what's going on here. And that's a space where there's been enormous progress, for example, in using AI. For analyzing the data for axion experiments, eventually this could be useful, but often it's much simpler. These things, like scanning through radio frequencies is much simpler than reconstructing all the events that was happening at the LHC. And the truth is that the much more challenging aspect of this is that you need to build a massive radio. Actually, we expect that to get to fully cover this range, you probably need to build a radio that is several meters cubed. And it's estimated that this will cost potentially up to like $100 million to actually get there. So AI so far, well, I guess depends who you are, has not been able to pull money out of thin air. So that would be like the main thing that is limiting these experiments at the moment. Not so much the analysis, just that we need to prove that these ideas work before it's a worthy endeavor for the community to build onto that. But if the analyses become very challenging, AI will be deployed because it has been in other areas of particle physics. I guess in terms of coming back to your question about a textbook, one thing that I would say is that for at least for myself, in terms of getting interested in these topics, if you go down this path by going through graduate school and things like this, you will eventually learn all of the techniques that you need to understand these things. And for me, at least, I think one of the things that really instilled in me the enjoyment of that was a lot of popular science books. And I don't know, I would think that like getting a sense for what's actually happening at the cutting edge is maybe a better way of getting at that without working through all of the technical details. Of course, that's a matter of taste. And for example, recently one of my colleagues, Dan Hooper, wrote an amazing book all about thinking about just like what's happening at the earlier stages of the universe and what we know about this. And I think at least I was told by my brother-in-law in very easy to understand language. And even there's more detailed books about the history of actually how all of these things were uncovered. And I think, learning that, of course, the mathematics and et cetera that we've learned about is integral to actually being able to do these calculations. But ultimately, these things are done by humans. And I think learning, a bit about the human story of these things as well, for me, is what drew me in initially, and ultimately is a key part of what keeps me around. So that's a bit of a hedge, because I don't know of a particularly great book that I think brings you right up to speed on these things, but Grant does. So, yeah.
I was just going to volunteer the book I usually give people who want to understand quantum field theory from a popular level is Sean Carroll's The Particle at the End of the Universe.
Beautiful. Okay, and he's an amazing communicator, of course, so that's a great suggestion. Thanks, Grant. Yeah.
Okay, great. In the interest of time, let's hold our questions for Nick to lunch or other coffee breaks and move on to our next speaker. Thank you very much.